As I'll start, yeah.
All right, everyone, thank you for coming today. I'd like to start by acknowledging the traditional custodians of the land on which University of Wollongong is situated. We pay our respects to the Aboriginal elders past and present, who are the knowledge holders and teachers. We acknowledge their continued spiritual and cultural connection to country. As we share knowledge, teaching, learning within this university, we also pay respect to the knowledge embedded forever within the Aboriginal custodianship of country. And today, our speaker is our very own Alan Nutman, who's been here for over 10 years, and he's interested in the crustal evolution, particularly in Archean. And today he'll be talking to us about the Uniformitarianism and the Eoarchean Steinman Trinity. So, thank you.
All right, thank you very much. So hands up, who's heard of a Steinman Trinity? Good. Oh, very good. Even one of the young ones has actually heard of it. So Steinman was a Germanic geologist. I'm not sure whether he was actually German, Swiss, or Austrian, who in the early 1900s recognized in the Alps this puzzling association of metaprototype, serpentinite, gabbro, basalt, and chert. And this became known as the Steinman Trinity. I think the first publication, all the publications are in German, was in 1906, I think, 1905, 1906. Nowadays, we'd actually recognize the Steinman Trinity as components of a disrupted ophiolite. In other words, rocks which have got caught up, preserved in the continental crust along a suture zone in a collisional orogenic event. So this shot here just shows a nice scene of contemplating the largest surviving chunk of Earth's Eoarchean mantle, which got trapped in the crust more than 3,750 million years ago. So, buttons don't work on your computer. Oh, I know what you have to do, yeah, that's right, okay. So, this paper has also got the, this talk has also got the business of uniformitarianism, and I haven't even had anything to drink yet. And this has been going on ad nauseum ever since the realization of plate tectonics in the late 1960s and the discovery of the first crustal Eoarchean rocks in 1971. So this here is an illustration from a Royal Society paper or meeting held in 1973. And so there's these sort of various ideas about how very early crust formed. You've got essentially uniformitarian ones, such as illustrated along the bottom there, where you had natural movements of the crust as separate plates of undefined size, so that you end up with convergent and divergent boundaries, which I've added for the convergent, I've added the sort of red arrows on the diagram there. On the other hand, you have various non-uniformitarian models for evolution of early crust. There's one from a Southern African geologist called McGregor from 1951, where you're looking at a completely different style of crustal evolution, which is basically vertical displacements with no lateral movements of the crust. So it could be McGregor 1951, or for example, Webb et al. 2020. So there's obviously very major differences in viewing how the earliest crust formed, and the best thing to go and do is to go and actually look at the older crust rather than try and model it. But that's my philosophy. So before I get started, I'd just like to thank two of my main co-workers. I've been working with a long time, Clark Friend. I've been working with him since 1976. I've been working with him for 45 years. Vicky Bennett in ANU, I've been working with her since 1989, 32 years. So maybe with Clark getting towards the Guinness Book of Records for continual scientific collaboration. So where are we going? We're going to go to southern West Greenland. So this is an oblique Google Earth image of the area. So it's a tract along that coast which is relatively ice-free. So you've got the inland ice up on the right there, Davis Strait on the left, in other words towards the west. A few satellite little ice caps around, but quite a lot of ice-free country, although the relief is quite steep in places. So there's the early Archean occurs as a tract running from that red dot up by the inland ice, famous locality called the Isosupracrustal Belt, and then it goes through a fjord system to the east of Nuuk town and disappears out to sea. I'll be focusing on one particular locality to start with called Narsak Headland, where we find evidence for this very odd Steinman Trinity. I'll also, at the end of the talk, go up to the Isosupracrustal Belt. So I've been in this area for a long time, so I've indicated my first day in the field, 23rd of June 1974, where I had rather a drastic introduction to field geology in Greenland as doing helicopter reconnaissance mapping, which is not a particularly relaxing activity. Anyway, so let's just go have a look. It's very fortuitous working in this area, even though you are you're not technically in the Arctic here, you're just below the Arctic Circle. But the capital of Greenland, Nuuk, is in the area, which is a good logistical base. It's very easy to get there. There's scheduled flights every day from Copenhagen in Denmark. So this is just a general view of the town with the old and the new. And then talking about the early Archean rocks, they disappear out into the Davis Strait as a series of, as an archipelago, just getting smaller and smaller islands until in fact the outermost Eoarchean is actually just on reefs, only exposed at low tide. The other end, up at the inland ice end, basically you get the old rocks just disappear underneath the ice cap, okay? But one can actually track them even under the ice cap. I've been doing a program of doing zircons from stream sediments, from rivers actually coming out from directly under the ice. And you can actually, by that, you can track that the Eoarchean does continue further north under the ice. And then we also have another locality. There's this sort of north of where the Eoarchean rocks disappear under the ice. There's on this Nun Attack here, sort of about, I don't know, 30 kilometers north of the last exposures of Eoarchean. This Nun Attack just consists of Mesoarchean metavolcanic rocks. They got an age of about 3,065 million years, something like that, quite young. But it's quite interesting because although this Nun Attack is just solid Meso-Archean rocks, it's actually littered with tunnelite erratic blocks, which must have come from under the ice. And in one of my bizarre moments, I decided I'd sample one of these. And thanks to GeoQuEST, I dated it at 3,830, showing again that there's actually very old crust, but hidden under the inland ice. So, although a lot of people here might think that we work on an enormous budget, actually for Greenland, we work on a very small budget. This is because since 1980s, we've been working independently of the survey, and we must travel light. So basically, we have got a very light, compact camp, but we don't stint ourselves. We eat fresh food. So for example, we take frozen meat from the supermarket in Nuuk, dump it in a snowbank or a cold stream. And so we do eat properly, and we eschew nasty things like instant coffee, make proper coffee, everything. So we can do this because we can get our camp, which is 3 people, 2 weeks food, into an A-Star helicopter. And this gives us something like 150-kilometer range from Nuuk. So that's our camp, all our personal belongings, everything for 3 people piled up there. And we can last 2 weeks, but still with the food reserved in case of bad weather and so on. On the other hand, the survey geologists, they take a whole lot of superfluous things into the field, like chairs, tables, generators, laptops, all that kind of stuff. And immediately the cost of your logistics double, because any camp move, you've got to have 2 flights instead of 1 flight. So we do a lot of coastal work. Basically, coastline is really great for geology. So we've done a lot borrowing boats from local contacts, and we've had some fairly epic journeys of sometimes over 100 kilometers in a boat like this. And again, this gives us great range and low budget, but we've had to stop doing it because since 2005, we actually had to have a Coxswain's license, which is only given out to local inhabitants. So we actually had to stop doing it. It's the same sort of bureaucracy that I know that people are dealing with here. And it was ridiculous because by 2005, already had 30 years experience of sailing in these sort of waters. So we've been doing mapping independently of the survey since 1984. So basically traversing by day and good old-fashioned inking in the evening, making maps by hand, as you can see in the tent there. And then we're not completely Luddites. We do actually, this is one of our published things. So this is a map of the whole of the Nuuk region that Clark and I have produced, a digital map. Basically, the map, if it's printed at full scale, would be about 2 meters long. And the area is about equivalent to the size of Switzerland that we've covered over the years. So on the map, we have all our detailed geological observations, and also all of our uranium-lead zircon geochronology. And this is just a little detail of the map. And this is the locality that we're first going to be dealing with, this Narsak locality on the headland with the red ring there. Nuuk, which is again the capital of Greenland, is just about at the top of the screen there, and it takes about an hour on the chartered speedboat to get round there. So first of all, I want to say something about difficulties about early Earth geology. Natural systems are naturally chaotic. So an analogy I like using is something like this shot from a residential area in the US where a twister has gone through and nearly everything has been destroyed. But for some weird reason, you just get one house standing there. It's the same with, of course, fire in Australia. You get the occasional freak occurrence of just one house standing in complete devastation around. So if you look at most of that destroyed stuff, which is what most of the early Archean crust looks like, you can get a very broad picture of the early Earth from geochemistry and isotopic studies. However, if you find those very rare little areas, the equivalent of the house still standing, you can get a lot more detailed information about the early Earth, and that represents much less than a trillionth of the Earth's present crust, that all the really key information about the very early Earth comes from. And the reason why everything has been sort of destroyed and mangled is that there have been several orogenic events in the Archean, and the high temperature metamorphism and ductile deformation just simply distorts and corrupts the earlier geological record. And as an example, up here on the left, we show one of these very rare lower strain areas up near Isua, where you can still see 3,500 million-year-old Dirite dikes marching across the countryside. However, in most places, when you look in the early Archean rocks, because of the very strong Neo-Archean tectonism that these have generally suffered, something like these 3,500 million-year-old dikes, they're just smeared out as parallel disruptive bands of amphibolite within what was the original host country rocks. So that's the sort of a setting, the kind of problems that we have to deal with. It is literally finding a needle in a haystack, and all the needles are not found in one field season. It's a very progressive, continual thing to find new sites of interest. So we're going to be looking at this NARSAC ultramafic body. It's just large enough that it can be seen from space 100 kilometers up. So the red arrow there shows actually a little sort of yellowish blob near the coastland of the NARSAC Peninsula, and that's the locality which we've that was of interest. So zooming in just on Google Earth imagery, that's the northern end of the body, and this is a little map I've made of it, which quite clearly shows that you've got, first of all, the so-called Steinman Trinity association of ultramafic rocks, so mantle dunite in this case. You've got some layered peridotite as well, you've got layered gabbro, and then you've got sort of cherty rocks, banded iron formation, and then skarny metavolcanic amphibolites. And all of those are actually enclosed within metatonalitic gneisses, broadly, for those of you who don't know what a tonalite is, broadly granitic rocks, which have got ages of over 3,700. So we've got several age constraints on these units. So actually managed to get a very rare metamorphic zircons out of the Dynamites themselves, where the Dynamites are a little bit more messed up, which are clearly Eoarchean at 3644. The whole of the body is encapsulated, enclosed, and intruded by fringing metatonalites, which, for example, one at the southern end of the boundary down on the coast has an age of 3747 plus or minus 9 at 95% confidence. But most importantly, something which was done with GeoQuEST funding is dating of a diorite dike, actually cutting the intruded into the mantle Dynamites. And that has got an age of 3768 plus or minus 20 million years, 95% confidence. So this is what I regard one of the most remarkable geological localities in the world. You'll probably disagree with me. This is a place where you can put 1 foot on the Eoarchean upper crust. So basically sedimentary rocks or the cherty things with some solidified basalt, skyny volcanic rocks on the other side, and then you can put your other foot on the Eoarchean mantle to the left there. So it's only actually exposed over, you know, a couple of tens of meters. Other places, you know where the boundary is, but it's actually hidden by sort of gravel and so on. Okay, so it is a remarkable locality because you got banged up against the Eoarchean upper crust. You got actual Eoarchean mantle. So this is actually within the mantle dunite, and this is Dirite dike, which dated with GeoQuEST funding, and it's got this, as you can see, this reaction halo hornblende, making a hornblendite around the edge of it, showing the reaction between the rather wet Dirite dike magma and what was originally and essentially anhydrous mantle dunite. Dunite, if you're not aware, it's an ultramafic rock which has got more than 90% olivine and about 10% or less of orthopyroxene and a smattering of other things in it as well. So this is a diorite, typical diorite, could be diorite of any age, plagioclase, a little bit of quartz, amphibole and biotite. Of course, it's now all metamorphic rock, but it is still quite a nice, clean diorite. When you start looking at the chemistry of the diorite, and this is what is affectionately known to geochemists as a spider plot, or if you want to be more formal, a multi-element plot, we've got an array of mostly trace elements along the bottom, and then in the logarithmic scale, the abundance you've actually measured in your rock is ratio to a model primitive mantle. And these have got various signatures which can tell you, or you can relate to modern geodynamic settings. So for example, if you look at something like a pure mid-ocean ridge basalt, it should have this sort of fairly smooth trend running something down like that. There, it might move up or down a bit on the diagram, but it's essentially free of some of these anomalies. And when we mean anomalies, it means there's sort of jumps in the concentration of one element relative to the neighboring one. And the most important jumps that you can see here is a negative titanium anomaly and the negative niobium and tantalum anomaly. And that is a classic signature of convergent plate boundary magnetism. And in this case, with the diorites, from their bulk element chemistry and the presence of these sort of negative anomalies, you're looking at fluid fluxing of a mantle wedge signature in order to get these geochemical patterns. And as comparison, I've put on some other of our very old rocks there as well. So, for example, up at this area, Isua by and Ice, a slightly younger diorite, and you can see it's got exactly the same pattern. And then also extremely rare gabbro from Isua with an age identical to that diorite, which has also got these negative titanium niobium tantalum anomalies, again showing this sort of arc-like convergent plate boundary signature. So this is, some of the Dynamites are actually amazingly fresh considering what they've been through. So here's a really nice Dynamite. So you've got olivine, spinel, and very tellingly, you've got pargasite. You've got a little bit of pargasite. So you can see we've got here. Never mind. You've got in the middle of the screen there, you've got things like this here, which I mean, sound like somebody in my classes now, whereas the olivine has got irregular fracture. You can see the cleavage developed in the pargasite. Pargasite is interesting because pargasite develops in the hydration process of the mantle wedge above the in the suprasubduction zone setting. So this is a dunite containing small amounts of pargasite. When you start looking at the chemistry of the Dynamites, they have this ultramafic discrimination diagram designed mostly to distinguish ultramafic rocks, which have got a mantle pedigree, versus ultramafic rocks, which are just cumulates, the dropping down of olivine and pyroxene crystals from a slowly cooling and crystallizing gabbroic magma in a big intrusion. So our two samples of the Narsak Dynamite there, they sit very nicely in the field of depleted mantle, Dynamites and Harzbergites. On the other hand, also from the same locality, we do have some layered peridotites, and they actually sit, again, they sit in the ultramafic cumulates field. But there's no doubt that we've actually got samples of mantle present at this locality. So when you start looking at the rare earth chemistry of these ultramafics, when you look at the Dynamites, they have got, not surprisingly, they're very depleted. They're very sort of residual compositions, but also very importantly, like abyssal peridotites. But when you start looking at light rare earths, you show a slight increase, kick up in abundance here, because if you just had simple melting of primitive mantle to give you depleted Dynamite compositions, then theoretically they should go off down like that there. And this is known from the study of modern abyssal peridotites, that this is due to some trapped refertilization within the mantle dunite by last vestiges of a percolating melt coming through it. On the other hand, when you start looking at the layered peridotite, which is rather higher in aluminium, and it's associated with layered gabbros, it's got a different pattern, and you can see a negative europium anomaly, which suggests there's been plagioclase fractionation coming out of it. This is a rather horrible bit of a sawtooth irregular pattern here, and that is probably because it's just done in a routine analytical setup in ALS, which don't necessarily come across such low abundant samples every day. So this is just a typical metagabbro. It's a little bit layered here and there, so you get some color index layering. It's a metagabbro now, so it now just consists of a granoplastic mixture of hornblende and plagioclase. But again, you can see quite a nice clean rock considering everything it's been through. This is where things start to get interesting, because when you actually look at these gabbros, they actually have a pattern very much like mid-ocean ridge basalt or back arc basalt. On the other hand, if you look at these arc-like gabbros and basalts in places like Isra, they've got this other completely different pattern here. And so here are 4 samples of the metagabbros, very similar patterns. The associated skarny metabasalt at that locality also shows the same pattern. So this is something rather different from what one sees throughout the rest of the Eoarchean record, where you generally have arc-like signatures for the gabbros and metabasalts. So going back again to our multi-element diagram, overall you're seeing, when you look at the gabbros, one is seeing something looking a bit like pure moor, but you are getting these small, for example, negative titanium anomalies, and also significant enrichment in elements like rubidium, potassium, and so on. So what this might mean is that we're not actually looking at mid-ocean ridge basalt, sensu stricto. We might be actually looking more like something like a back arc basalt, which can actually show some of these more subtle anomalies, subtle titanium negative anomalies and so on. So here we are, we're back at the locality again with a different perspective. So here are sedimentary rocks, here's our skarny altered metabasalts, and bang, here's the mantle, here's the Eoarchean mantle, bang, up against them. So it's a fairly clean rock again, mostly quartz, and this is a very high iron amphibole called Dirite, which can be quite common in metamorphism of iron-rich sedimentary rocks. So basically, it's a rather iron-rich quartzite would be the best way of describing it. So you end up with essentially quartz, grunerite, and a little bit of magnetite as well. So when we look at the chemistry of them, I was hoping to get what we call a pure seawater signature. So seawater, for time immemorial, actually has got a very diagnostic rare earth and yttrium trace element signature. So this, in this case, it's basically normalized to post-Archean as shale. So basically, even when you go back and look at Isra, 3,700 million year old banded iron formation, when you look at our single occurrence of preserved stromatolites at 3,700 million years, so this is a dolomitic lithology, this is an iron and quartz rich lithology, these have got the classic seawater signature. If you analyzed a coral from the Great Barrier Reef, you would get exactly the same signature, apart from the European anomaly would be different because of a different oxidation state of waters then as opposed to now. So I was hoping to get this signature, but no, we got something completely different, but it wasn't a complete disaster. So here's our Narsak siliceous sedimentary rock, and this is a better preserved 3,700 million year old siliceous sedimentary rock, where the rock is well enough preserved, you can actually see it's getting some kind of volcanic input into it. So there seems to be a similar pattern developing there. So when we look at some of the other geochemical signatures, for example, this classic diagram here, which is used to distinguish basalts formed in different geodynamic settings. So if you're looking at things like morb, emorb, ocean island basalts. If you're looking at in the Archean record at these things called komatiites, those are all melts which are formed by decompressional, adiabatic decompressional dry melting of the mantle. On the other hand, you have a field over here due to enrichment in thorium. This is the arc field of mafic, volcanic, and plutonic rocks, which you could look at anything from arc rocks forming today all the way back to the beginning of the Eoarchean, and you'll find that they sit up here. So as an example, this is the field for Isra 3,700 million year old. We even have bonanites, which are down here, basalts here, and andesites up there. Okay. However, when one actually looks at this Narsak locality, we actually get to sort of a bipartite division. So nicely, of course, the Narsak Dirite, which is intruding the Dunites, it actually sits up in the sort of where andesites you'd expect to sit. Andesites, Dirite should sit up there. So clearly a very strong arc signature of fluid fluxing. On the other hand, when we actually go and look at the gabbros, they actually seem to form a bit of a trend running across this way, actually more or less emanating from where N Morb is, but sort of trending off towards the arc field. So I think there is a good case to be made that we are looking at here, we're looking at straightforward arc magmatism. Here we're actually looking at something more of a back arc basin character. So that's looking at this Steinman Trinity on Narsak Peninsula. Let's go to Isua, Balian and ice, and look at some other ultramafic rocks which reveal something important about early Earth, and they feed very directly into whether one's looking at the so-called mobile lid plate tectonic regime, or this what's called a stagnant lid thing. So this is a nice picture of Isua taken from helicopter late in the summer when there's just been a little dusting of snow. It'll melt off again, but it does make life a bit difficult when this happens. So what we're going to do is we're going to look, this is the northwest end of Isua, and there you've got a whole series of imbricated lithologies, which is people who've worked on convergent clay boundaries will be very familiar. You have integrated, intercalated slivers of bonanites. You've got foliatic basalts of arc-like geochemical signatures. You've got andesitic grey whackers. You've got andesites, and you've got cherts. And these are all just slightly older than 3,700 million years old. However, as a sliver, again, within the sequence here, shown in purple, you've got ultramafic rocks. Most of these shown in the less intense color, they are thoroughly tectonized, messed around, schists consisting of serpentine, talc, some orthoamphiboles, but within them, you actually got some lenses of peridotite here, which are preserving the original olivine-bearing assemblages. So this is a sort of a view from up on the hills here, looking over this way. And so you've got your bonanites, you've got this pod here of peridotites, and then you've got your arc foliates on the other side. So when one actually looks within the preserved metaperidotites there, which contain olivine, one has this very significant assemblage, which is olivine plus antigerite, which is a serpentine mineral, plus one of these bizarre, very rare minerals called titanochondrodite, which is converting to titanoplinohumite. So this is a view of the sort of scale at which these discoveries are made. That's 20 microns. So this is a very large grain here of the titanochronomite or titanochondrite. So all of maybe 60 microns long. So this is this kind of scale that important discoveries are made. So this is very important because when you're looking at the conditions under which these sort of assemblages are stable, you're actually looking at pressures somewhere in the order of 2.6 gigapascals at sort of temperatures somewhere between 500 650 degrees Celsius. So this is the first discovery in the world of very old ultra high pressure metamorphic assemblages. So why is this important? This is a review paper by Brown and Johnson of metamorphic conditions throughout Earth history. I've bastardized it a bit because I've condensed the scales of the along here, so that's very condensed for the Phanerozoic. Here we are from the Neoproterozoic all the way through into the early Paleo-Archean, which I've plotted on the data that Brown and Johnson got from the literature. So prior to that, Brown and Johnson had only put on a few of these ones here, which were known about. But what we now have is we have ultra high pressure metamorphism at something over 3,700 million years, whereas the previously oldest recorded occurrence of this was somewhere in the Mesoproterozoic. So basically, that's over 2 billion years older than the previous occurrence. So why is this important? The only place where these assemblages are known to form on Earth are in relation to subduction channels at convergent plate boundaries. So what happens is these rocks forming under a very low temperature pressure apparent gradient, and then they have been very quickly somehow regurgitated up, using a technical term, into the crust, where they've been locked in and preserved. So what we're seeing here is the kind of assemblage locally preserved in a sliver of mantle rocks, which are suggestive that they have sometime been down in some form of a subduction system to great depth. The other interesting thing that you'll see about this diagram, which I'll come onto the next slide, is if one actually looks at this compilation of Brown and Johnson, actually as time goes by, apparently the apparent geothermal gradient, maximum geothermal gradient of metamorphism actually increased with time. So this is a bit counter-intuitive because the Earth has definitely been cooling throughout its history. So why on earth is this happening? Well, I think I've got a very simple explanation for that. If you look at the modern heat flow map of the Earth, you can actually see that, of course, continental crust and the thick subcontinental lithospheric mantle is actually a very good thermal insulator. So I think simply what's going on is that very early in Earth's history, you had much less continental crust around as an insulator. So that is represented here by this bowl of tomato soup with just one crouton in. Nowadays, you have got, here's our Earth, and you've got all these croutons floating around, croutons, cratons, same difference, okay? And they are actually making a much better thermal insulator. So although the Earth is cooler now, it's actually, less efficient in losing heat because of the insulating effect of that continental crust. And you only have to go to bed at the night when you don't know whether to put the blanket on or not to actually experience that. Because obviously if the bit of your body where the blanket is across, the continental crust, heats up more than your toes, which is sticking out from underneath the blanket. So I think this is also another proxy for showing the growth of continental crust through time. So take away message about rare Eoarchean sample in Greenland. All samples of the earliest geological record are small, diverse, and vanishingly small areas are providing detailed information. And often the information on the sort of geological scale is coming from outcrops of only a few squares or tens of squares of meters. And crucial information also comes at the micron scale from thin sections or from the interiors of individual grains. So basically, if you actually look at Greenland's metamorphic record integrated with the evidence, you can see things like the equivalent of the Steinman Trinity. The case, I think, can be very strongly made that you'll see right back at the beginning of the geological record, you're seeing some form of convergent plate boundary processes and then collisional orogeny. You're not having this model, what's called static list system, where Earth has got the single lithosphere plate all the way around it, which is being impacted by vertical magmatism from underneath. So I would say that ancient geodynamic resembled plate tectonics. It wasn't the same. And most importantly, there's no need to invoke non-uniformitarian scenarios for the Archean Earth. Let's finish off. It's true, we're getting ice for our evening gin and tonic. Okay, that's it.
So unfortunately, we're a bit short on time, so we'll just have time for one question.
Just a quick one, Alan,
Yeah.
thank you very much for the
Yeah.
talk. So, okay, no need to invoke a
Uniformitarian, yeah.
uniformitarianism model, that's fine. What about the thickness of the crust at the time compared to modern day crust? I mean, your Trinity has the juxtaposition of mantle,
Yeah.
deep sea, mid-ocean rich rocks, and
Yeah.
a small area. Does that mean that the crust was very thin?
One can't tell that from that kind of just get there, that kind of locality, because they're just simply fragments of an earlier process which are now sort of a mega enclave within surrounding granitic rocks. However, some of the metamorphic assemblages that we do have, we have these things called high pressure granulites, which they're produced by double thickening or more than double tectonic thickening of the crust. So you've got to have quite reasonable amount of crustal thickness being generated. So you weren't dealing, with some amazingly thin skin, because to get these sort of assemblages, and also not shown on there, also within Isua, a few localities we have got, and these were discovered by some other people in the early 1980s. One's actually got classic so-called Barovian metamorphic assemblages. So that is coexistence of kyanite and staurolite, again, which is a classic sort of metamorphic assemblage developed during collisional orogeny with thickening of the crust.
I've got one question from chat. It says, great stuff, Alan. Thanks for all the exotic pictures. Have you ever come across anything suggesting glacial diamictites in your Archean Greenland work?
No, because one problem is that all of our rocks are metamorphosed, And that kind of subtlety is very difficult to establish. We think we're doing very well when we can recognize a rock has got a sedimentary protolith. It's that sort of level often. Or I'll go a little bit more fair than that. One will be able to say, okay, we think this is a meta-grey-whacker. This is obviously a banded iron formation. But finding these sort of subtleties, it's only at this locality, for our stromatolite locality, where we've been able to reconstruct, if you like, something which would be satisfactory to stratigraphers in this room. All right.
All right. Thank you again, Alan.
Okay. All right. Let's get it out.
I'm going to close that first.
Yes, I see Lei was watching in China.
Mm-hmm. All right.
I think it's pull it out. Okay, good. Oh, there we go. Thanks.
Thank you. Thank you very much.